Good afternoon. I am Mariusz Dąbrowski, the president of the Jerzy Stelmach Eureka Foundation, which deals with interactive education and popularization of the frontal scientific research. Gather scientists, and therefore for a couple of days, we offer you lectures and debates under the project Science and Technology Progress Closer to the Society. As in particular, the session which is entitled Dark Universe, Problems of Contemporary Cosmology. Our project is co-financed by the Polish Ministry of Science and Higher Education, and its aim is to bring the achievements of outstanding scientists to the general public. So today we will be summarizing what has already been somehow presented during the 4 lectures given by our guests collected together during today's discussion session, which is entitled When Will Dark Matter and Dark Energy Be Discovered? We have heard already some generalities, some lectures about dark matter and dark energy. Today we want to discuss vividly what are the opinions of my colleagues about the possible discovery of these 2 entities called dark matter and dark energy. So our discussion will be attended by our colleagues. First, our lecturers. First, welcome very warmly Professor Vincenzo Salzano from Szczecin Cosmology Group. Hello, Vincenzo.
Hello.
He was talking on Saturday last week about dark matter. Hello, Professor Salvatore Capozziello.
Hello, everyone.
Who was talking about the dark energy in the universe and problems related to that also on last Saturday. And we also have heard the lecture of Professor Leandros Perivolaropoulos, who is also with us. Hello, Leandros.
Hello, it's a pleasure to be here. Thank you for the invitation.
Thank you. And Professor Leandros Perivolaropoulos told us about the cosmological tests and the cosmological tensions yesterday. I told you also yesterday about the age of the universe and how deep we could investigate the universe and with what tools. Today we are going to focus on our summary, kind of a vivid discussion about what would be the future of these 2 phenomena and what our experts expect could happen in physics, cosmology, astrophysics, in the context of the problems above mentioned in the future. Let me start with the questions. I have one first question to Professor Salvatore Capozziello. What is the Big Bang in your personal understanding, and why do we think that the universe expands? And can we somehow replace Big Bang with something different? Professor Capozziello.
Okay, thank you very much, Marius, for these very important questions. So the Big Bang is essentially the beginning of space and time. it has been, for the first time, announced, this kind of theory, by Georges Lemaitre. Georges Lemaitre was a priest from Belgium, and he was also very interested in science. And he made a very interesting statement connected with the fact that if the universe is expanding at certain point, it should also start at a certain point. So the Big Bang is the point in which the universe has no time and space, and all the matter is concentrated. Technically, the Big Bang is a singularity. It means that the standard laws of physics are not working in the Big Bang. So the main point, you can state that at certain point existed a Big Bang because the universe is expanding. Coming to the second question, the main probe of the fact that the universe is expanding has been given by Edwin Hubble. Edwin Hubble was the first that realized that very far galaxies are receding from us because according with their distance, their velocity is improving. This, this phenomenon can be tested by the Doppler effect. In fact, you can take into account the velocity of a galaxy and then connect such a velocity with the fact that the emission and absorption light emitted by the galaxies are moving toward the red. It is called redshift. And then, since this kind of object, this kind of probe is for all galaxies, the statement, the final statement by Edwin Hubble in 1929 was that the universe is expanding. So Lemaitre, considering this, in some sense, rewind the problem, considering the fact that if you take a universe that is expanding, this kind of expansion should start at certain point. And then he enunciated the theory of the Big Bang. So the Big Bang is the point at which the universe and then the space-time start to expand.
But can we replace Big Bang? Because it's kind of a mysterious point, okay? Everything was somehow created. Are there any theories briefly which can say, oh, well, it's a kind of a stage, not necessarily the beginning? Or do you think there is something behind Big Bang?
Okay, so this is a very fundamental question, but also a very speculative question, because there are some models which try to avoid the Big Bang, because saying that there is a singularity at the very beginning means more or less nothing. So there are several models, for example, the bouncing models of the universe, or the universe connected with inflation that probably we will discuss in this meeting, in which the Big Bang singularity is avoided. So the Big Bang should be nothing else but the fact that the universe is passing through a transition era, and then this kind of singularity means that the physical states of the matter is different. So this kind of situation could happen also in the future, and this depends on the fact that the universe could at certain point start to contract again. So it is very important to understand if the universe is expanding forever, or if the universe at certain point will stop this expansion and start to bounce, and then this kind of Big Bang or this kind of singularity could be in some sense reproduced also in the future. So this kind of singularity could be in the past and in the future. By the way, there are some approach in particular related with some fundamental theories, for example, the string theories and other theories, which try to avoid the Big Bang. So they say the Big Bang is nothing else but a state of the universe which is very concentrated, but is not a singularity that, according with the fields which are present in the early universe, can be avoided.
Okay, thank you very much. Yes, let us move to the description of the universe. Okay, it is something full of galaxies, full of stars, full of any other celestial objects. It was said that the universe is considered to be homogeneous and isotropic. But if we look at the sky, there are more stars in that direction, in the other direction. Professor Perivolaropoulos, what is meant by this homogeneity and isotropy? Because we don't see it in the night sky. Why do we say that it's homogeneous and isotropic?
Okay, thank you. This is a very interesting question to discuss. Before I try to address this question, I'd like to say something in the previous question about the Big Bang.
Yes,
very
okay.
brief comment. I want to say that the Big Bang, as pointed out by Professor Capozziello, is a singularity, which means we have infinities. Quantities go to infinity, like the density of matter, the density of the energy of the universe goes to infinity, and the scale factor, for example, of the universe goes to 0, and we have various infinities appearing in this moment. Now, we know that in physics, every theory which has infinities in it must be incorrect, must be incomplete. So this tells us basically that
we cannot measure infinite
because exactly the infinity is outside of the numbers. It's not measurable. It's something which is beyond the physical world we live in. We know this doesn't exist as a physical measurement. So this means that the theory which leads to the Big Bang is an incomplete theory. General relativity, which predicts this Big Bang, is indeed an incomplete theory, and also predicts other singularities, like the black hole singularity, etc. This tells us that this is an incomplete theory, needs to be completed by something else. And the obvious thing to complete this theory with is quantum gravity, quantum effects. We know that in quantum mechanics, there is the uncertainty principle which prohibits us from going to very small distances, to very small scales, to infinitely small scales, because of the uncertainty principle. And so, in fact, this tells us that we need to complete our theory of gravity, general relativity, with a new ingredient, which will be called, we call it already quantum gravity, but we don't have any idea exactly what it is. There are some theories which try to do that, but with not clear success, like string theory. So the problem is there. We need to complete general relativity, but we don't yet know exactly how to incorporate quantum mechanics so that the Big Bang becomes something which is physically measurable, will be replaced from a singularity to become something simple and easily understood as a finite, measurable physical number.
So the creation of the universe like this is kind of, kind of a parallel, but in fact, it just says that something is behind this, like other physics or something.
Something is missing there, something is missing, and probably is related to quantum mechanics, and that's the most likely thing that is missing. And we need to find this to complete our theory. That's what is the result. Now, coming back to what you answered, asked about the homogeneity, it's clear that the universe, if we see around us, we see nothing homogeneous. We see, for example, a chair, we see some stars in the sky, we see visible points, like. So it's clear that the approximation does not seem to be very good because we see different things around us. Our everyday experience is not really homogeneous. However, we should never believe our eyes because the science has various ways to detect things without being visible directly to us. And so one thing that cosmology has managed to go very deeply in the sky and see much more additional stars than we actually see by our eye. If you go very deeply in the sky we call it higher redshifts or very early times of the universe, you see so many stars and so many galaxies. And if you could see it with your eye, you would see something which was more or less homogeneous. On the average, on very large scales, if you are able to see much bigger part of the universe, you will see that on the average, it becomes homogeneous, more or less the same number of stars in every or galaxies in some area in the sky. It exists. So on the average, the universe is a homogeneous system, an isotropic. But the question is, what does it mean isotropic, and what does it mean homogeneous? These are two different words we should clarify. Homogeneous is something which is the same at every point in space. For example, you can imagine an arrow, you can imagine a space full of arrows, and every point will have an arrow pointing in the same direction, so it will be the same in all places of the universe. On the other hand, isotropic means to be the same in all directions. So it cannot be the same arrow everywhere, because if it was an arrow, you wouldn't see the same things around an arrow. You would see arrows pointing in a direction. For example, I could show you here, if you can see my screen. Can you see my screen?
Yes.
Almost, yes.
Yeah, you see here, for example, an example. You see a wall with bricks, which is a homogeneous system. They all point in one direction. And the other thing is an isotropic system, which is the same in all directions. If you combine the two, then you get the system of galaxies of the universe on very large scales, which you see in this picture here. And this is from my talk of yesterday. So you see a system which is homogeneous and isotropic on very large scales. And this isotropic and homogeneous system is not only obtained by mapping the position of galaxies on very large scales, but also from the cosmic microwave background, which I also discussed in my talk yesterday, which is an isotropic bath of radiation, which comes to us from the early times of the universe, which is extremely isotropic around us. And we believe that this is a picture of the universe at the very early times, at times much smaller than its present age, when the atoms were formed for the first time. And the universe, the baby universe at this time, which comes to us from all directions with the same temperature, the same form of radiation, we think that in fact this is a baby universe, this is very isotropic. So this is the so-called cosmological principle, which states that the universe on large scales, and at early times also, was a very extremely homogeneous and isotropic system. And that's why we're also very lucky that it is this way, because we can describe it. If the universe was not isotropic and homogeneous, we would have difficulty to describe such a very complicated system. We are very lucky that this universe on the large scales is so simple, and we have simple equations, like the Friedmann equations that I showed here, I showed in my talk yesterday, which are so simple, just a scale factor, which allows us to describe the large-scale background evolution of the universe. So it's a very fortunate thing for us to be able to have this excellent simplification, to be able to describe the universe.
So in principle, philosophically, it fulfills the Copernican view that there is no privileged place in the universe. We are not unique, okay? There are many places which from which you see the universe similar, okay? That's
true. I mean, in principle, one can interpret the Hubble's law, for example, that we are in the center of the universe and all galaxies recede from us. That would be very special and very strange kind of approach. The simplest and more natural approach is that we are not in the center of the universe, but all observers observe the same Hubble expansion, and this can only be explained if the universe is expanding as a homogeneous and isotropic system.
Okay, another question to you, if you don't mind. There is Hubble test and say supernova test, which was bringing people to the say notion of dark energy. What does the Hubble test tells us about, and the supernova test tells us, and what was the meaning of the breakthrough of the first one and the second one?
Okay.
Okay.
Okay,
go ahead.
Salvatore, yes, you may also say.
Yeah. Okay. So the idea is this one. Can you see my screen?
Not yet.
Yet, can you see it?
Oh yes, now it's
very good. Okay, so the Hubble test is something very straightforward. As you can see here, what you have is that the universe is expanding, and then according with the equation that Leandros showed before, it means that in any direction and with the same rate, it is expanding. And then this means essentially that all directions are the same. So the Hubble test means that there is a certain scale at which the universe has the same density and appear in the same way in all directions. So according with this, you have the homogeneity and the isotropy. Regarding the fact that at certain point you have to take into account the dark energy, it is connected with the fact that you can imagine that such an expansion is going on and it is decelerating. While what people have said, what people saw some years ago is that instead of decelerating, is accelerating. How they get this information? Because according to the luminosity distance connected with the supernovae was fainter than expected. So the luminosity distance is something very straightforward. Imagine that you have an object emitting a certain amount of light, so you can calculate the distance of such an object taking into account the number of photons, so the amount of luminosity that you get on with your telescope in particular. So according to the luminosity, to this luminosity distance, this kind of supernova was fainter than you can expect. And at the end of the day, they get this kind of situation. I will show you in a moment. I show you in a moment. Okay, they get this kind of situation. So these dots are the supernovae. And you can have that this kind of curve is the fact that you get a deceleration. While they got that this kind of object, instead of decelerating, accelerate, because in this Hubble diagram, the Hubble diagram, as we discussed the last time, was the fact that the recession velocity of a galaxy is proportional to the distance. Instead of decelerating, they accelerate. So according with this, people, in order to understand what is this source of this acceleration, they invented the story of the dark energy. So the dark energy can be considered simply a sort of a dark fluid which is acting with an inverse pressure, and this kind of pressure is making the universe accelerating instead of decelerating. Imagine that you are exercitating a pressure. If this pressure is negative, what is going on is that your universe is expanding in an accelerated way. So essentially, this is the mystery that we, at the moment, we can see the phenomenon, but we have no fundamental counterpart for such a phenomenon. So we have no fundamental particle or something related with this that can explain this kind of phenomenon.
Thank you very much. I don't know, Professor Leandros, do you want to add something? Or?
Yeah, very briefly, I could probably add that, in fact, what we're going to measure, basically, is the scale factor of the universe, which tells us what is the expansion of the universe, as I talked about in my talk yesterday. Now, to measure the scale factor of the universe, we need two ingredients: to measure the redshift and distances to very far away objects. Distances we can measure using supernova, for example, or other standard candles, as discussed in my talk yesterday. Now, the key point that this measurement of Z, of the redshift and the distance, leads us to two important things. First of all, is that we have an expanding universe, which also is accelerating, increasing the rate with time, the expansion rate with time. And now, to achieve this, we need something which has repulsive gravitational properties. And the obvious thing that has this repulsive gravitational properties is something which has negative pressure, and this should be the property of the fluid, which will induce this repulsive gravity. Now, what does it mean, negative pressure? It means that if you put this thing in a box, like if you put matter and gas in the box, it pushes outside, pushes the box. If you put springs in a box, little springs which connect the walls of the box, then they pull the box inside. So they have negative pressure. That is, it has tension. And the substance of the universe, which has this property, negative pressure, like the cosmological constant, is this kind of substance. This tends to pull inwards, and so this kind of object has the property of asking repulsive gravity, and then leading to the so-called acceleration at very large scales. But this repulsive gravity acts on very large distances. We cannot detect it here on Earth or in the solar system because it's a very weak coefficient. It's proportional to the distance, and you have to go to very large distances, cosmological distances, to dominate over the attractive part of gravity that we know. So if you go that far away, you end up having this repulsive kind of effect, which causes the accelerating expansion.
Thank God, because otherwise it will be very difficult to live with repulsive gravity.
That's right. We would go upwards.
Okay. Yes, repulsive gravity would really be a problem for us.
It exists on Earth also, but it's so small that we cannot detect it. Even if you had the most sensitive instruments, it's such a small term in the gravitational force that cannot be there, but it exists. In principle, if we had a very extremely sensitive instrument, we could detect some correction in Newton's law, which would correspond to the cosmological constant, the repulsive term.
Yes, fortunately, it's not large. Okay, let me now let me now switch into our another colleague, Professor Salzano. We were talking a lot about dark energy. Now let us switch into dark matter. My question is the following. Does the fact that the night sky is dark refer to the problem of dark matter? It's a kind of a provocative question. So can you say what you think about such kind of a approach?
We are talking about different types of darknesses here, because the problem you posed is actually known as Olber's paradox. So if the universe is infinite, so there are so infinite number of stars, how is it possible that we don't see them? And actually the paradox is solved because the universe has not existed forever. It's not eternal. As it was said, there was a starting point. So the universe has an age, first of all. So it's not eternal. At least it has 14 billions of years, which is quite a lot, but it's not eternal. And also we have to consider that light, which we always talk about light like the fastest thing which we can know, and that's true. But although it's very, very fast, it has a finite speed, which is huge, 300,000 kilometers per second, but it is finite. So it may happen that light didn't have time to reach us. So that's why there are so many dark spots in the sky. Not only this, there are also other two things. That, as it was said, there is dark energy, which is accelerating the expansion of the universe. And this means, said in very simple terms, that light needs more and more time to recover the space which has been extended by the accelerated expansion of the universe. And last point, because of I also spoke about it on Saturday of this thing which is called redshift, which is the stretching of light electromagnetic waves due to expansion and the velocities. Light is stretched towards some ranges which we cannot see. So actually we can see that if we look to the sky with high sensitivity telescopes which are in the space like James Webb and others, and if we have a very long exposure time, and if we look not only in the so-called visible band but also in the microwave or the infrared, we see many, many more objects than what we can see at naked eyes. So it's a lot of ingredients. Actually, it's a lot of things which we understand quite well, so that we can explain why the sky is not like in daily life.
Disappeared.
Okay.
Dark energy, dark matter. Because dark matter is dark because does not interact with light, so we cannot see it. But dark energy is dark because we don't know what it is. So there is. Can you hear me?
Yes, yes. Now we can. Yes, yes.
Okay.
There was some break.
Okay.
Yes. Please continue.
Yeah. Okay. So. So the question about what is dark matter is that we don't know what it is exactly.
But it doesn't have anything to do with the darkness of the night sky, I understand. This is what Professor Salzano wanted to tell us, I think. He is now hanging a bit. So let me, okay, are you back, Vincenzo? Yes, can you hear me?
I'm here, yes.
Yes, because
yes.
sometimes we have a break in transmission from you. Okay, let me ask another question because I want to ask you more and more questions, and we still are mid of the meeting. Let me ask about cosmological tests, cosmological probes. Can we really trust in cosmological tests? Because in fact, what we have in experiments on Earth is very close, and we basically know that the physics must be a kind of a known while we dealing with the laboratory experiments on Earth. How about the cosmological distances and far distant objects which are somewhere? Can we really trust cosmological probes that we measure the things appropriately and not kind of assuming something which is not justified? What do you think about it?
Can I ask? Can I answer?
Okay, yes, if Salvatore wants, yes.
Okay. So, in some sense, in this moment of the history of science, we can trust cosmological probe because we are living the precision cosmology epoch. So you can trust or not, but the point is that the experiments are so precise in this moment that they, in some sense, can be compared with experiments in particle physics. So according with this, we can trust into the cosmological probe. So the cosmological probe are very good. On the other hand, the theory in order to interpret this cosmological probe should be something controversial because you cannot reproduce the experiment like in the case of standard physics. So according with this, you can trust because they are very precise from one side. From the other side, most of them can be addressed by several theories, by several models. So the important point is how to discriminate among concurring models. And then according with this, we have to, in some sense, we have a big problem with the interpretation. For example, the big issues that we are discussing, dark energy and dark matter, we know for sure that the effects exist. So dark matter allows us the clustering of structure. Dark energy allows us this interpretation of the expansion. But at fundamental level, we don't know what they are because we have several interpretations according with this. So the problem, according with me, is that we can trust in cosmological probes, but we have a big problem, big issue with interpretation.
Any other voice about this?
May I add something also, please?
Yes, please, yes.
Thank you.
Because it's a provocative question.
I will agree partially with Professor Capozziello in the sense that, in fact, we live in precision cosmology. And in fact, the experiments, the observations of cosmology have become very precise. However, these observations, unfortunately, are not very accurate because you have to make a distinction between precision and accuracy.
Yes,
this means that these observations indeed have very small error bars, but it's not clear what are their hidden systematic problems. Some assumptions made during the experiment or the observation, which could be incorrect. For example, we know that even though all our measurements are extremely precise, we know that many measurements we have for cosmology are not accurate. They are not true. So they say they have small error bars, but in fact, the true value is very, very much different. So it's very much out of the error bars. And a big example from this is the well-known Hubble tension. We have different measurements of the Hubble parameter using different kinds of assumptions and methods. And they all swear, they all promise to us, they are extremely accurate. They're extremely precise. And they measure the Hubble constant with very big precision. But then, if you compare them with each other, you find a huge difference, a 5 sigma difference, or even 6 sigma nowadays, which means that the probability that they disagree because of statistics is 1 part in a million and even smaller. How can these precise measurements disagree by such a huge amount? And the answer is because they are not accurate. Some of them make wrong assumptions. They assume that the objects they have are the good way to measure things, but they are not. Like, for example, the group of Adam Rees and collaborators, they will convince you that they do everything perfectly. And they measure Hubble constant to a very big accuracy to be 73.04 plus or minus 1 kilometers per second per Bragg parsec. The other group from Planck, they will tell you they also measure it very precisely and extremely well. And they will swear that the value is 67 plus or minus 0.5. Obviously, one of the two groups is incorrect. We're not sure which one, but it's clear that we have to understand what assumptions one of the two groups made and actually led to the incorrect, inaccurate result. So even though it's precise, we have to make multiple different kinds of systems should agree before we believe the result. In many cases, multiple systems agree. For example, the accelerating expansion has been measured with many different probes, and they all agree on that. The universe indeed is accelerating its expansion. There is no doubt about that, because many different approaches indeed agree on this result. That we believe. So we think it's accurate. But other results in cosmology, which are not in agreement with different probes, are in fact precise, but not accurate.
Okay, thank you very much. I don't know if somebody wants to add. Vincenzo, would you like to add something to this? I don't know. I think it's okay.
I just wanted to say maybe none of them is correct because Professor Leandros Perivolaropoulos was saying we have these two measurements. Which one of them is correct? We don't know. Maybe none of them is correct. I'm just saying just in a provocative way. And I was also wanted to add, although Professor Capozziello is my scientific godfather, just not to go against him, but I guess that nowadays we are talking too much, we are focusing too much on this precision cosmology, because precision, okay, respect to what? To 100 years ago, yes. 50 years ago, yes. But we don't have, I guess that we don't have to forget that cosmology, modern cosmology, is actually quite young, because we had concept in theory which we had to wait like decades before to be checked. For example, we are talking now about dark energy. Dark energy was, well, the accelerated expansion of the universe was discovered when I was in my first year of the university. So I'm probably the one, I belong to the generation who has been hearing about dark energy like it was normal. And although I don't think I'm young, but I'm quite young. So what I mean to say is that there will be a lot of funny things probably happening in the future, but I would not trust too much precision cosmology nowadays.
Okay, let us put full stop on this. It's kind of inspirative for the audience to actually think of this in the near future. We will come back to these questions at the end of this discussion. So let me just make some room for this. Okay, now again the question to Professor Salzano. It was said about these cosmological probes. There are kind of typical tests. I would like you to just briefly say what is the merit in simple terms of the notions like supernova, cosmic chronometers, gamma ray bursts, and also baryon acoustic oscillations. So can you say in simple terms to the audience what are they about?
Okay. You can hear me, right? Now you
Yes,
can
yes,
hear
we
me.
can hear you very well. Yes.
Okay.
So just because
So
I mean,
it's
these tests are mentioned, and okay, they were already somehow mentioned and explained, but I would like you to repeat in some simple terms because this is summary discussion. Okay, so key issues for the audience which may not necessarily have heard the previous talks.
it's a bit hard to
I
condensate
know.
everything, but
I'm inviting
I can
experts. Yes, okay.
but I can say that I mean most of the cosmological probes which we use nowadays, they are based on the concept of distances. Not only the luminosity distance which was cited by Professor Capozziello before, which is the distance which can be inferred, for example, with supernovae. It can be inferred also for gamma ray bursts, but there is a problem, as it was said in his talk on Saturday. Supernovae are standard candles. It means that even if they are so far, we know what is the intrinsic luminosity. So measuring the luminosity here, we can compare them and we can calculate the distance. Gamma ray bursts, unfortunately, are not standard candles. They are very far from being standard candles because supernovae, you can stretch them in luminosity in time and you see that they follow the same pattern, luminosity pattern in time. Gamma ray bursts are totally different. Each of them has some peculiarities, so it's not very easy. But in principle, also gamma ray bursts can be used to measure distances very far. Cosmic chronometers is a term which is given to some specific galaxies, some elliptical galaxies. So apparently they are the most boring. They don't have these features like spirals and bars. They look like just bulge of stars with different shapes from circular to elliptical, a bit more flattened. But what is peculiar? Why they are called cosmic chronometers? Because scientists I guess it was in the early 90s, noticed something that when you take light from these galaxies, there is a very typical feature. So they see that there is a break in the so-called light spectrum. And because galaxies are made of stars, and we know quite well how stars are born, how they evolve, and so on, the scientists noticed that the amplitude of this break, which technically is called D4000 line break, depends on the age of the stars or the stellar populations. So what they did was, let's take these galaxies, let us measure what is the magnitude of this break, and then let us compare it with our models. In this way, they were able to say, oh, this galaxy is XX old, And they were able to create these cosmic chronometers. That's why they are called in this way, because they were able to correlate some features with some evolutionary time, real time. And in this way, they were able to, for example, calculate the Hubble rate. And about BAO, baryon acoustic oscillation, the story is even more complicated, because they are related to the CMB, and they could even be related to the very early moments of the history of our universe. But they are very peculiar, because I want to share in this case quickly. I want to share quickly my screen, so probably you can see. So just to let you know what are BAO, baryon acoustic oscillation. If you look at this image, and I ask you, do you think that when you look at the sky during the night, or if you look at any image, the sky, the stars, or the galaxies are distributed in such a way? Well, everybody would say no, because it's clear here that if you look enough, you see that there are some circles, no? Now I ask you, if you look at this other image, this looks more like normal, the images which we see taken from telescopes, no? If you imagine each of these like a star or a galaxy, I don't see any pattern. But I can tell you that the only difference between this and this is that here there are like 1,000 of these circles instead of 100. But here there is a pattern. There are a lot of these circles. And what we have done, with not me personally, but the scientific community, what we started to calculate is the distance between all the galaxies. And then we arrived to this. It is a technical plot, but just to let you understand what it is, here we are calculating how many times a given distance is appearing in the sky. And as you can see here, there is a clear peak. And this peak is telling us that there is a typical characteristic distance between galaxies in the sky, which is much more frequent. And it is the radius of these circles. Now, the origin of these distances, as I said, is related to early time physics of the universe. But these can be also used as a cosmological probe, because we can calculate how much it is, and then we can measure it at different distances from us. And the comparison between how much should be and how much it looks tell us what is the distance. So all these luminosity distance, this is called angular diameter distance, help us to understand better what is the cosmological model which is behind our universe.
Okay, thank you very much.
Just to say briefly.
Yeah, very, very nice. I hope that our audience watching us on YouTube also, and future audience will take it for granted and understand. I would like, because we are running out of time, I have a few questions, and I want in particular make these provocative questions or summarizing questions to each of you. But one thing which was not very strongly mentioned, I just did it in my talk yesterday, was cosmological inflation. There is such a question, kind of again provocative, because you, I think, hardly mentioned this. I mentioned this and showed just the ordinary equation, and ordinary inflation with the money and cosmological inflation as an effect. But can you say if this cosmological inflation has anything to do with dark matter or dark energy? I don't know, Professor Salvatore Capozziello, maybe first.
Okay.
Yeah.
So in principle, they are the inflation is working in early universe, and it means that it is nothing else. Nothing else. It is an accelerated expansion in the early universe, and it has been invoked in order to understand why the universe is so isotropic and so.
But this is this accelerated expansion is due to what?
Is due to a different form of matter, which is called the scalar field. So it means that the matter, as we know,
but it effectively exhibit negative pressure or not?
Yeah, yes, it must exhibit a negative pressure. So it is more or less similar from a phenomenological, from a dynamical point of view to the dark energy, but it is in the early universe. And why? But the inflation, in some sense, is better understood with respect to the dark energy, because there are some fundamental theories which can explain inflation in a very straightforward way. Why? Because as soon as the matter is undergoing a sort of phase transition, in which you have that the interactions that we see, it means gravitation, electromagnetism, weak force, and strong force, as they appear today, at certain point in the early universe, all of them can be the same interaction. This kind of interaction can be connected with the scalar field. And this kind of scalar field, which is a very different form of matter, can give rise to the inflation. So now we don't know today if dark energy and dark matter are in some sense related with this early process. In some sense, you can say very likely they could be connected, but at the moment we have no final evidence that dark energy and dark matter could be connected directly with inflationary behavior. I want just to say this, that there is a very nice sentence by Francis Bacon, the philosopher, the ancient philosopher, which says that the beginning of a science can be connected with botanic. The end of the science is connected with the dynamics. So for the modern cosmology, we are in the phase of botanic, because we are just collecting data, and we have to derive at a certain point a full history of the universe. So the dream of any cosmologist is trying to get a consistent history, starting from the very beginning, and then from the Big Bang up to the dark energy epoch. But at the moment, it is nothing else but a patchwork in which we are just collecting several eras, and we would like to understand if there is some unifying picture for the universe.
Anyone else wanted to add something?
Can I add something to this? Which was,
yeah, if you want, because I want to switch to the, say, summarizing questions. It will be kind of a quiz for you, if you don't mind. I have, I mean, we could, of course, talk more about other issues like cosmic microwave background, neutrino background, gravitational wave background. It was mentioned already, so I'm referring our audience to the lectures given throughout this last weekend and on Monday. But now I would like to ask kind of your opinions about dark matter, dark energy. So my first question, you may answer this just in short, yes, no, or I think this or that. And it would be even best because we are just closing. I mean, we have like 10 or 15 minutes maximum. So let us first ask. Let me first ask the following question. Do you believe, as cosmologists, scientists, do you believe in dark matter and dark energy? What I mean by that is that you do not think that it's a fake, as a kind of artificial thing which is present in contemporary science. Let me start with Salvatore. Okay, what you say?
I am very sincere. I don't believe that dark energy and dark matter is a true problem. Very likely we are missing something very fundamental, and I can say that at the moment there are no new particles that can explain dark energy and dark matter. Very likely, but this is just my opinion, they could be connected with the behavior of the gravitational field at a very large scale. So it should be connected with gravity.
Okay, thank you very much. You are experts. I'm asking about your opinions. Full stop. Leandros, how about you?
Yeah, I think that as far as dark matter is concerned, I tend to understand that it may not be existing, of course, because it may be a manifestation of gravity, but I personally believe it exists. That's my own opinion, that there's more evidence that dark matter exists, and it's not, the effects we see are not a manifestation of modified gravity, because dark matter has been seen in various ways, like gravitational lensing. We have seen the bullet cluster, which shows that there is something there which looks like matter. It provides gravitational effects. And there are also some more direct ways that dark matter has been seen through its gravitational only effect. So I personally believe, but I recognize that it may be that also it could be gravitational, purely gravitational effects with no real matter existing there, so some modified gravity. Now, as far as dark energy is concerned, there I tend to understand that in fact lambda is now the prevailing model, cosmological constant is one that most people believe, but I personally would tend to believe that in fact it's a modified gravity effect. That is, in fact, gravity on these very large scales has some deviations from general relativity. And what we recently has been seen also by some experiments, like from the DESI experiment, which gives some hints for dynamical dark energy, as I talked about in my talk. There seem to be some modifications which take us away from cosmological constant, from very precise baryon acoustic oscillation experiment. And these modifications are very strange because they point to a particular form of the equation of state of the dark energy which crosses the phantom divide line, the W equal to -1 line. And if this is true, no simple theory of general relativity can reproduce, no field of general relativity can reproduce this kind of crossing. So we need modified gravity. And we had a paper a couple of days ago when we saw how to reconstruct this kind of modified gravity, which will be consistent with the very recent finding of DESI, which found some dynamical forms of dark energy.
Okay, Vincenzo, how about you?
My personal opinion is that we observe something, and the dark matter and dark energy, in their most mainstream version, are probably the easiest solution to interpret what we see. If they are real particles, real field, or just we need a generalized theory of gravity, this I don't know.
Okay.
And I guess that is good. And I guess it's good that I don't know, because this means that I have things to study and to work for the next years.
Okay. You will earn some money, which is good. Okay. Okay. Yes, that's also a kind of a motivation to actually to have something to investigate. Okay, the next series of questions is the following series of answers, I would say, comments from you. Do you, I mean, somehow you mentioned this already, but I want you to make clear kind of a statement. Do you think that the problem of dark matter and dark energy refer to observations or to theory or neither or both? Okay, theory, observations, neither or both. Salvatore, maybe let's make the same round.
Okay. So in my opinion, are both. It is connected with observations and very likely, I agree with Leandros, we have a precise observation, but not accurate, because we have to interpret this, and probably we don't know. And it is also connected with theory, because we need at certain point some theories in which all the patchwork of this puzzle should be connected in some way. And at the moment, we have to be very humble and honest. We have no theory and no observation that can fix definitely the problem.
Okay, thank you very much. Very clear answer. Professor Leandros, how about you?
Yes, okay. I tend to agree with Professor Capozziello, which is a very nice point that he made. In fact, we can never really understand something unless you combine the theory and the observation. And right now, I mean, the approach that most people consider for the progress of physics is that first you have the observations, which are accurate and precise. And after you agree with this, then you make a theory which tends to make this coherent and understandable. Right now, at this stage, we're at a stage which we have precise measurements, but they are not yet surely accurate yet. So first we have to converge to accurate measurements about dark energy, for example, to understand how it behaves, and then make a theory. And this is very similar to what happened with Kepler's law, for example, when Kepler was trying to parameterize the motions of the planets using some simple parameterizations, because Kepler's law has some parameterizations of what was really happening in the solar system. Once he managed to obtain these accurate parameterizations, which are basically the three Kepler's law, then Newton was able to interpret them and embed them in a theory, which was actually the full understanding of gravity, of Newtonian gravity at the time. Of course, general relativity changed this, but at the time, first came observations, and then came the theory, which actually was able to make comprehensive the measurements in the context of a theoretical model. Now, of course, at the later stage, when Einstein came, it was one of the very rare examples in physics where the reverse happened. Einstein came in with some Gedanken experiments, and he was such a powerful mind. It was also a mature situation when he first made the theory, general relativity, and then came the verification from experiment. But that's a very rare thing to happen. Usually, progress in physics happens the other way around. We make observations, we make parameterizations like Kepler's law, and then the theory comes to make this whole thing consistent under a theoretical framework. So we're now at the stage where we are somehow constructing Kepler's laws. We're trying to find parameterizations which describe the data in a more concise manner. And hopefully, once we agree with that, once we find good parameterizations where all different probes of cosmology agree, then we find our Kepler's law, then some Newton will come and combine them, all these observations, in a theory which will explain both dark matter and dark energy.
Very interesting approach. I like it. Okay, give me the floor to Professor Vincenzo. How about you? Would you like to add your opinion?
Yeah, I agree with both professors. I would say that the problem of dark matter and dark energy is us, because we make observations, we clean the data, we make assumptions on how to clean the data, and then we are the ones who interpret this data. And so, in principle, I agree with both Professor Capozziello and Professor Perivolaropoulos. I don't know if it is 50-50. I trust more what the data are saying, and I see more variability, more possibilities in the theoretical part. But in general, I would say that both of them must be taken care.
Okay, thank you very much. And the last question of this discussion, if you don't mind, some kind of future predictions related to dark matter and dark energy. I can remember the famous Stephen Hawking book, The Short History of Time, when he wrote that the unified theory of all the interactions will be created finally before the end of the 20th century. It was close to this, and he just speculated. I would like you to speculate a bit about when, in fact, will the dark matter and dark energy when will be discovered, or when will the problem of dark matter and the dark energy be solved? So please try to be kind of accurate. Tell me, in 10 years, in 20 years, never, or it's a missing problem, so I don't care, or simply say 50 years, 100 years. Okay, let's start now again with Professor Salvatore.
Can I this time, because I have an answer, my answer is not accurate, but I hope that they will be solved after my retirement, but before I'm dead. Because after my retirement, because I want something to work about, but before I'm dead, because I'm very curious to know what is the solution of this.
Excellent answer, which is very funny, and I like it. Yes, you may answer whatever your approach. I don't mind, and I guess audience also don't. They don't mind this. So yes, we have it from Professor Salzano. Who is next? Okay, Salvatore. Yes.
Okay. Okay, so I want to report two examples, very important example. The first is the problem of ether, and the other is the problem of phlogiston. Both of them was very important in the history of science. In the 19th century, everyone believed in the existence of ether. And several people like Michelson and Morley try to understand what is this kind of ether. At certain point, a guy stand up, certain Albert Einstein, and demonstrated that ether cannot exist because you can formulate a theory which don't need ether. In the same way, there was the problem of the phlogiston. The phlogiston was a fluid that was transporting the heat. And in the 17th and in the 18th century, this kind of phlogiston was very common in every book of science. At certain point arrived Ludwig Boltzmann that found out that you don't need the phlogiston because he got by thermodynamics the answer to the story. So I think that we are exactly in the same situation. So dark energy and dark matter are connected to the problem that we are not understanding phenomenology and what is going on. So we are very poor, both from the point of view of data and from the point of view of theory, because we are not capable of addressing in a self-consistent way all the phenomenology, also if this phenomenology exists. So I think that as soon as we have a very deep and very good bulk of data from one side, and we have a self-consistent theory, I think that more or less, in my opinion, in 10 years we could solve the problem. I'm very optimistic. And then after this, we can say if really dark matter and dark energy exist. But at the moment, I am connected very well with the people in Gran Sasso, and they made the club. The club was called the Zero Result Experiment Club. Because all these people are searching for dark matter for direct detection. The Dama experiment, the Xenon experiment, dark side experiment. But at the moment, they have improved a lot their precision, but they have no final probe for dark matter. So at the end of the day, if you are not capable of seeing something, I think that in a very, very straightforward way, you can say that this does not exist. If you cannot see something, it does not exist. Albert Einstein made the same with ether. He said that why you cannot detect ether? Because ether does not exist. So I think that we're exactly in the same situation.
Excellent answer, and I especially like this 10 years. It will be like Professor Salzano said, maybe after your retirement, but still alive. So you will you fit this kind of a spirit. Okay, last but not least, Professor Leandros, how do you think about?
Okay. Thank you for the question. It's a very interesting question. I will try to be very precise, but I'm not going to be accurate. So I will say what I think, but probably it will not be accurate. So my personal opinion is that it will take about 50 years for the discovery of and the understanding of dark matter and dark energy. And this I say because of two reasons. First of all, I understand that during the past 27 years, even though precision cosmology has developed extremely, we are more or less back to the original idea of cosmological constant. During these last 27 years, there have been various claims about dynamical dark energy, but more or less the standard model remains exactly lambda CDM, and still we don't have a very good understanding of the details of the observations of dark energy. And same with dark matter. I mean, there has been huge efforts for the last 35 years to discover this particle, and despite the very well constraining experiments, we still have no clue what is this particle and what is dark matter. So the last 25 to 35 years, practically there has not been any major progress in cosmology, despite of the fact that, in fact, lots of improvement has been done in the methods. So the problem is really very difficult. And in fact, it's discouraging that I see that recently funding has been reducing. I see that the US is dropping out from various projects, which are very ambitious for cosmology and for general, for cosmological science and science in general. So based on this, trying to project from what happened during the last 25 to 35 years, I'm a bit pessimistic. That's why I'm saying I anticipate about 50 years and perhaps even more for the not only for the discovery, for the parameterization, I said about the new Kepler's laws, but also for the theory, because we also need afterwards the theory, which will explain these parameterized properties of dark matter and dark energy. So that's my own opinion.
Okay, thank you very much. So I'm not sure Vincenzo will be happy with this answer, but hopefully there will
I
be
hope to
some
be
solution.
still alive in 50 years.
Still alive, yes, hopefully. Yes, generally, I like the idea that the two problems will just disappear like ether or phlogiston. So this is what I like. My personal view is maybe close to this, that maybe these problems are kind of gradually may be disappearing. And I somehow feel like Vincenzo, that I would like to have this problem solved before I would maybe still can do in this life on Earth. Thank you very much for your comments, for your answers. And finalizing this meeting, I would like to mention again, it's in Polish, but we would like to acknowledge the support of the Polish Ministry of Science and Higher Education, and also please take into account that you were the hosts of the Jerzy Stelmach Eureka Foundation from Szczecin, Poland. Thank you very much also for the attendance to our guests, professors Salzano, Perivolaropoulos, and Salvatore Capozziello. Please listen our films which are recorded on Eureka Foundation YouTube channel. The address is www.youtube.com/Fundacja Eureka in Polish. I would like to again draw your attention to these films. A lot of them are now in English. Our Polish audience, I would like to ensure that there will be a translation of this discussion and the lectures showing up soon, so you will be able to somehow hint all the details in your own language. And thank you very much, everybody attending. I cannot see a question. Okay, maybe there is one. Okay, there are some thanks, in particular to Professor Capozziello, from a friend from our Szczecin Cosmology Group. And there are no questions from YouTube as far as I can see. Thank you very much. And I wish you all a good evening, and see you during the next discussion fora. Thank you very much.
Good. Thank you.
Nice.
Thank you very much. Thank you. It was very nice being here.
Bye-bye. Thank you.